Welcome to today's webinar, the Delta T90 House, Net Positive, Nearly Passive. This webinar is brought to you by Open Architecture Collaborative, the AIA's Housing Knowledge Community, and EDI International. I'm Steve Schreiber. I'm the facilitator for today's webinar. You will be earning one AIA learning unit for this webinar. Today's presenter is Matt Lutz, an architect in the state of Vermont and an associate professor of architecture at Norwich University. He teaches courses in passive environmental design as well as hands-on design build studios that address issues of environmental stewardship. Professor Lutz's research agenda is concentrated on the feasibility of affordable, high-performance housing for cold climates. The learning objectives for today include understanding the forces that drive the demand for affordable housing in Vermont and discuss how these forces relate to the region, discussing the benefits, challenges, and opportunities posed by modular prefab, describing a general strategy for balancing the reduction of heat loss and upfront costs with architectural delight, and demonstrating techniques for cost saving relative to high-performance residential design for cold climates. Today we'll learn how a small university in Vermont developed a high-performance, solar-powered dwelling priced competitively to address the issues of affordable housing in cold climates. Among other honors, the small dwelling is credited with consuming the least amount of energy with the smallest photovoltaic array at Solar Decathlon 2013. Some logistics. We will be entertaining questions throughout the webinar. And the way that this works is that you can submit them, written questions, via the chat box, which you can see on the right of the screen. Content-related questions will be answered during the question and answer towards the end of the webinar as time permits. This presentation is protected by the U.S. and international copyright laws. Reproduction, distribution, display, and use of the presentation without written permission of the speaker is prohibited. AIA Knowledge is a registered provider with the American Institute of Architects Continuing Education System. Credits earned on completion of this program will be reported to AIA CES for AIA members. Certificates of completion for both AIA members and non-AIA members are available upon request. So please join me in welcoming Matt Lutz.
Hello, everyone. Thanks for tuning in. We're going to start by looking at some images of, oh, sorry, let me show my screen. Okay, we're going to start by looking at some images of the Delta T90, but first this term, Delta T90, stands for change in temperature of 90 degrees. So we were trying to make a house that could be energy balanced annually with the change in temperature of the outdoor temperature of -20 with maintaining an interior temperature of 70 degrees, hence the 90. So, oops, having trouble forwarding. Okay, so this project got started by looking at just some data in Vermont and what it would take to make an affordable high-performance house here. So Vermont ranks 6th in the nation in terms of annual heating demand. We use about 48 billion BTUs for annual heating demand. And about 80% of that heating demand is sourced from petroleum-based products. So about 63% of the housing stock that we have in Vermont was built prior to 1979. So that means things like lead-based paint, really leaky construction, maybe asbestos, and things like that. About 82% of the households here earning under $41,000 pay about a third of their income, or sorry, pay more than a third of their income for their housing needs. So when you couple this back with the fact that we live in a place that demands a lot of heat, and that heat is coming from petroleum products, you start getting this sort of financial planning wild card for folks that are earning under $41,000. And then you couple that with the fact that of the existing affordable housing stock for the folks that are making under 41,000, there's only about 18% of that is available for those households making that income. So this is the team that worked on this project, and actually the team is quite a bit larger. The extended team is quite a bit larger than this. So the project was really started to address the affordable housing need in Vermont, but we used the Solar Decathlon 2013 as a platform to get the project noticed and to get the issues that it would bring up sort of out in the public. To use the Solar Decathlon as a national and international stage. So this is essentially the what the house looks like. It's 1,000 square feet, super insulated, and comes with a 5.8 kilowatt integrated PV array. And the target that we were trying to hit is to make this affordable by a household with 2 wage earners, both making minimum wage. And that equals about $41,000 annual. So in addition to that criteria, we also had to satisfy the Solar Decathlon criteria, which means that the house has to be shippable. So we had to build this house in Vermont and then ship it to California and comply with all of the Solar Decathlon rules and regulations. So the outline that you're seeing around the building here, this sort of gray outline, hope you can see my cursor, that outline is the solar envelope that the house couldn't breach. This is generally how the house is laid out. We have 2 modules, an east module and a west module. So the east module has the kitchen, the bathroom, the auxiliary room, and all of the mechanical utilities. And the majority of the wiring harness is in the east module. The west module, where the living room, office, and bedroom are, it's basically just a dumb box. It's got electrical outlets in it, and that's it. So this is an extended exploded axon. So you can see the PV array integrated to it, and you're seeing these things like water tanks and the tank covers and the ADA compliant ramp on the west module and on the south side of the house. Those were really there specifically for the Solar Decathlon. So we built this house in a modular housing factory in East Montpelier, Vermont, on an assembly line. So our students worked with the folks in the factory to build the house. And this factory has been in business for about 35 years. They do some high performance housing and have since this time just been doing more and more this kind of work. So the Solar Decathlon, why we felt this project would be a good fit for the Solar Decathlon, why it would be a good stage to talk about affordable housing on, is because the Solar Decathlon is since its inaugural event in 2002 has really been moving more toward the issue of affordability. So one of the criteria of the Solar Decathlon is that you get points if you keep the house at 249,000 or below. The other agenda that it has is to really push innovation, and I think this is where the Decathlon event really excels. Is that folks go to the event and they learn all about these new and forthcoming technologies. That innovation comes with a cost, though. So, for example, in 2009, the most expensive house was $849,000, or about $849 a square foot. The least expensive house in 2011 was $249,000. So in 2011, I think there was more than one team that satisfied that $249,000 benchmark, which is great. But in Vermont, that still doesn't work. Like, that's still out of reach of so many people. So our benchmark for this project was to make a house that could be high performance, net zero, for about 150 to 160,000. The official estimate from NREL and the Department of Energy from the Solar Decathlon 2013 is that our house would cost 168,000, and that's on a that estimate is taken on a national average, so it's not specific to New England. I should mention that after this project was completed, we went back and looked at how we would redo this house if it were just staying in Vermont, if we didn't have to, if we didn't have to ship it to California and compete in the competition, and pretty confident that we could get it down to 150. So this is a wall section through the house on the left of your screen, and on the right of your screen you'll see the Passive House Planning Package spreadsheet for the insulation values. So if we start at the base, we have a couple ganged LVLs with 11 inches of dense packed cellulose at 4 pounds per square foot. Moving up to the wall, we have a double stud wall with dense packed cellulose. And then on the outside of the wall, we have 2 inches of mineral wool. Only plywood was used for the walls and roof sheathing. It's a little more air permeable than OSB and stands up to the weather better. If we move up to the roof, we've got an LVL for the rim joist, and then 12 or 11 1/4 inches of dense packed cellulose, and 4 inches of mineral wool on the roof, and that's covered by a TPO membrane. And on top of the TPO membrane, we adhesive bonded a thin film PV array. Note the single top plate and just the single LVL. So we used high performance framing on this. There are no headers over the windows. That LVL is responsible for making the spans over the window openings. So we're getting about R39 in the floor and R46 for the walls, and then R60 3.7 for the floor. And of course, this takes into account for the framing in the wall section. Then we see this is a section through the window. Note how the mineral wool insulation wraps down the wall and butts into the window frame. From a thermal study we did in Therm, software Therm, we verified that this was the logical place for to put the window. It also gives your cat a really nice place to sit here because you've got a decent windowsill, and it's just having these deep walls helps the wall not read paper thin if the window is in the middle of the wall. So this is a cross section through the house. So really, what we have is a really simple box. You know, some folks on the team were saying that just from an energy modeling standpoint, that the skylight was a real indulgence, an overindulgence because of, you know, maybe some of the heat loss that we'd see from it. But in terms of daylighting, the house is really well daylit. This is from the software Therm, just looking at where we were going to see thermal bridging. We really tried to eliminate as much as possible by wrapping the whole house in mineral wool. But you can see right here in the middle at the floor, this is where the east module would connect over to the west module. Right in the middle of the house, this ganged LVO beam, we've got some serious thermal bridging going on. Because of the competition, we never really planned to insulate or wrap the underside of the house with mineral wool. And if the house had come back to Vermont instead of going to Ohio, we probably would have wrapped it wrap the underside of the floor. So this is the first floor plan that we'll look at. You can see the south side of the house here with the main entry door. The kitchen lands right along this wall. But something unique about the house is that there is no mechanical room. You know, there's this contradiction between the term passive house and what that really means. When we think of a passive house, we think of a house that's getting its energy from just passive sources. It seems like more and more all the technology that's going into passive houses means that the mechanical room is getting bigger and bigger, and the mechanical systems are getting more and more complex. So we really wanted to make this thing really super simple. So this little boxy room right here is actually where the stackable washer and dryer goes, and then right in back of the washer and dryer, mounted to the wall, is an on-demand water heater. Directly above that in the ceiling is this 15,000 BTU ductless ceiling-mounted mini-split heat pump. The exterior condenser is right here. We just drop the lines through the floor in an insulated chase, then connect it to the condenser. So yeah, we can pretty much eliminate any space taken up for HVAC. And then the heating recovery ventilation unit, we used 3 pairs of the Lunos E2 system. So we have 1 pair back here in the on the north side of the house that satisfies the bedroom fresh air. And then we have a pair between the living room and the kitchen. And then we have a pair in the bathroom. So this is continuous ventilation for the bathroom. So this is some of the energy modeling. When this is plugged into the Passive House Planning package, one assumption that we made going into this is that we would, because we were going to super air seal this, that we would have about 0.3 air changes per hour at 50 pascals. And based on the weather data that we had from Burlington, Vermont, and the wall system and everything else, we thought we'd be at about 9.1 kBTUs per square foot annual. So you can see we're still pretty far away from the passive house standard, which is 4.75, but we're still so much better than what the average house is in Vermont by like a factor of 4. So although we didn't meet the passive house standard, we're still really really confident in the design. After the competition, the house was being shipped to Springfield, Ohio, to become part of the Frank Lloyd Wright's Westcott Center for Architecture and Design. So plugging it into that weather data, you can see now we're pretty close to the passive house standard. And then here's some window data. So if we look at our overall transmission losses to the overall heat gains that we have in the house, we're doing pretty well. It starts looking like, you know, that south-facing window, we probably would have maybe been better off with not doing such a high-performance window there, even letting in a little more heat gain, and then having a solar curtain over it for the winter. So moving down the factory, the house can be completed in 12 days. So you sign the contract. As soon as the house starts, you take ownership of it as it moves out of the factory door 12 days later. So you can see on the assembly line here, this is the east module with all the smart stuff in it, and here's the west module that's basically just an open box with some electrical outlets in it. So it rides on these rails and these rollers. So it moves from station to station and is pushed by a little lawnmower without a mowing deck on it. The first station where the house starts is this framing deck, and the floor frame is started. All the electrical is laid in place. The lumber that we used was all graded lumber, so if you look really carefully here, you can see that even the crowns are indicated. So the house goes together really super tight, and the person that's doing that's leading the framing of this work in the crew, this is what he does every day. So the work happens really fast, and the quality is extraordinary. Laying some adhesive down over the joists. You can see the bundle of cables. So when this after we get the decking on and the walls start going up, this thing will be raised off the ground, and so someone can get under there comfortably and wire the house. We air sealed the house just so much. We're fanatical about air sealing. And remember that when we get towards the end of the presentation. So if you look at this little box that's along the this joint right here, so this is where the plumbing will drop through and connect to plumbing underground. This little access port right here is what is eventually going to connect the electrical utilities from the east module to the west module. It took 2 students about 45 minutes to air seal this with tape. So at the end, by the end of the project, I estimated that we had 2 students who were, not full-time carpenters, air sealing the house about 8 hours for two students. So in terms of time, it really wasn't that much time to do this extra step. And working in the factory, there are just so many advantages to it. We were doing this in November, so there was a little bit of snow, and it was that sort of icy season where we're getting a little layer of ice on everything. Working in the factory, everyone stays warm. The house never gets wet, so none of the framing, none of the sheathing materials, the insulation, it all stays perfectly dry during construction. So let's see if this will work. This is in the factory. So this main panel here, this is the east wall of the house where the bathroom is going to end up. You can see the double stud construction going on. So these are our students and folks from the factory working, and they actually move this fast when they're in the factory. Take a break once in a while. But you can see the moisture resistant sheetrock for the bathroom. And so once the house, the wall is crane lifted and put on the wall, it just moves down the assembly line. So after we put the walls on, we then put another layer of tape right here between the sill and the rim joist that went around. The kitchen window from the exterior. Again, no header. We're going to drop the roof on this in a minute. You'll see the LVL coming on board. The efficiency of the factory is pretty incredible. So any piece of wood that's under 16 inches gets put into this hopper. The factory then burns it for heat, and anything that's left over that they can't burn in a timely manner goes out to the back lot, and folks from the community come and pick it up. All the sheetrock waste is stacked into these nice little tidy pallets, and is then sent back to the gypsum manufacturer, recycled and made into new gypsum wallboard. It's estimated that the factory is recycling about 100,000 square feet of sheetrock annually. So now we're looking at the roof ceiling system for one of the modules, and what you're looking at here is the sheetrock right here. So the sheetrock is actually laid down first, and then the framing is put on top of the sheetrock, and then a guy comes along with an adhesive gun, and adhesive bonds the sides of the joists down to the sheetrock. The whole roof system is then lifted by a crane, an overhead crane, and then dropped on top of the building. What's really interesting about this process is that the house is insulated from the outside inward. So air sealing things like electrical boxes down here gets really easy to do. So we seal all the joints with fire fire sealant, but then we also have the opportunity to tape any joints. One drawback of this is, that you can see from right here, well, actually maybe you can't see it, is that this little joint right here. So on the outside of the wall, the sheetrock ends up extending in places all the way out to the outside wall. So there's that little thermal bridge. We weren't really too concerned about it because we did have the mineral wool breaking that thermal bridge. So this is the main plumbing wall in the house. So this boxed opening right here is where the ceiling-mounted mini-split heat pump would be supplying air out to this side, and the return air is on the opposite side of the wall. This took an 8-hour day on one day, and then 2 hours the next morning to finish the plumbing and get the electrical in. All the plumbing is on this one common wall too. So an exploded section, just giving an idea of what the insulation system looks like again. So we see the cellulose for the wall system and then covered in mineral wool. We are wrapping the whole house in mineral wool. After the house is wrapped in mineral wool, we then put a rain screen compliant house wrap on it and then taped those joints. So really what we're doing here is we're trying to air seal the inside of the house, and then we're air sealing the outside of the house too. We're trying to build this super airtight house, and then wrap it in this rain screen. So sealing up all the electrical breaches for the outside of the building. We then strapped it using these 6-inch long screws. So we had to go through the 3/4 inch strapping, through the 2-inch mineral wool, and then hit the stud, which was sometimes challenging. So this is showing the junction box, or the access port between the east module and the west module. So you can see these little tap connectors that are labeled. There's a hole drilled through the rim joist, which is over here, if you can see my cursor. We just pull the cable through and then plug the modules in together, and that's wiring the house on site. So this access port ended up being sort of a big thermal breach at the end of the project, though. We trucked the house over from East Montpelier to Northfield, about 30 miles or 20 miles one morning, and then set the house in about 3 hours. Over the next few weeks, we started to clad the building and tighten it up. Remember that we had to take this all back apart and then ship it to California. The exterior is locally harvested white cedar. It's 5/4 inches and treated with an oil. So you can see on the back side of the house here are the heat recovery ventilation units. These two work in tandem. So the one on the west module will be bringing in fresh air. And then at the same time, the one on the east module is exhausting stale air. As it's exhausting that stale air, it's capturing the heat from the house in a ceramic core. Then after 70 seconds, the fans in these switch directions. Now this east one, which was expelling stale air, is bringing in fresh air over that warm ceramic core and preheating it before it comes into the house. So these things, these heat recovery ventilation units use little 7-watt fans to drive the system. So you know, all 3 pairs of these are using you know, like what a fluorescent bulb would use. And they run continuously. It took us a couple of days to put the thin film photovoltaic array on. You can see one of the panels here. We put a tape, a double stick adhesive tape on it, a pretty high performance tape, and laid them down. It took about the same amount of time to do the wiring as it did sticking the PVs down. It's really just sort of a plug and chug system until you get to the junction box. So the house on its path over to California, we had to take a slightly longer route. The trucking company originally wanted to go through Colorado. However, I guess the altitude wouldn't comply with the window seals on our project, so they took the southern route. When we got to California, this is the site of the Solar Decathlon project. We set the house up. Happy to say we were the first team out of 17 teams to have a completed lockable house. We were also the first team to satisfy the NREL code compliance and code check, and to have a tourable house. The house went together really, really easily. Some of the issues that we had on site were just the limited space under the house to work the plumbing in. But you know, great opportunities like Brad is seeing here don't come along that often. So I think everyone got a lot out of that. So this is the completed house as it was presented at Solar Decathlon 2013. You can see the shutters on the outside of the house. In the passive house planning package, we accommodated for these shutters to reduce our solar heat gain in the heating months. So the spacing and the depth and the size of these louvers are all tuned for to block radiant gain in the cooling months. We actually, interesting note that one of the criticisms that we got during the Solar Decathlon from the judges were that these shutters were not automated, so we didn't have a motor driving them to open and close them for heat gain. We suggested we could just call the neighbor and ask them to come over and do them for us. This is an interior shot of the house. The wide-angle lens, granted, it is helping make this feel bigger than it is, but because of the daylight and the open floor plan, it really feels a lot bigger than 1,000 square feet, and actually it's just about 900 square feet interior. The living room. You'll notice this joint right here up at the ceiling. That's actually an LED lighting system, and that's how we're plugging up the gap where the modules come together in the house, because again the house had to come back apart. We used a 3/4 inch plywood for the finished flooring. That was covered with an obnoxious number of layers of whey-based polyurethane. So it's basically a zero VOC polyurethane. The kitchen, looking toward the living room. One of the rear bedrooms. We used a triple pane tilt and turn high performance passive house compliant window selection in the house. This is the master bedroom with a big closet, exterior door. You can see the skylight leading into the bathroom. So there's actually, you know, especially when the shades on or the shutters on the east, south, and west sides are pulled, the daylighting in the house is just so even. The bathroom using marine grade plywood throughout and a cork floor. So this is Solar Decathlon 13 held in Irvine, California. This is the first time that the event was held in California. And if you look down the row of houses, here, you'll see the Delta T90 house. It sort of looks like the garage of the Czech Republic house here. The Czech Republic's house was a beautiful house, but it took up the entire footprint of the Solar Decathlon site. So ours just really took up just the about half of it, because we're just showing the house really. And the Czech Republic house had a lot of exterior decks and porches and so on and so forth. So we did not win the Solar Decathlon event. In fact, we came in 12th out of 17. So although first place would have been great, we did exactly what we wanted to do in the competition, which is showing that we could make a really delightful, high-performance house that was really affordable. And the folks that really toured the house got it. Like they were really getting that message and really appreciating it. I think a lot of the folks that are coming to the event really appreciate seeing the new things, the innovation that's happening. The concern is, though, that folks are leaving saying, "Yeah, this is great, but we're never going to be able to afford it." I think that's where folks were sort of seeing the middle ground of the Delta T90 house. So the winner of the 2013 event, the Team Austria, made this just absolutely stunning project. And in terms of performance, this thing really performed. They didn't show up with a huge PV array. They had a moderately sized PV array and squeezed every ounce of energy out of it. And the overall performance of the house was extraordinary. But when we fall back from the performance a little bit, we can see that you can get a Delta T90 house and have $100,000 in pocket for one of these. The inside of the house, again, was just absolutely stunning. Another highly innovative project was University of North Carolina at Charlotte's house. They used an innovative new proprietary concrete system for the house. So the thermal mass was great, and again, just absolutely stunning inside. But this was 2 Delta T90 houses and a new Ducati motorcycle. So again, it's sort of difficult to compare so many houses together when there's so much spread in cost. But when we look at we'll look at the performance data in a little bit, and this all sort of starts to make sense. So the inside of the UNC house. So here are some numbers. And so here are all the teams. And if we're going to look at overall house consumption. So how much energy did the houses use throughout the competition? And so the Norwich team, the Delta T90 house, used the least amount of power throughout the whole competition. And throughout the time, we actually stayed net positive. So we actually produced 15 kilowatt hours over. So that worked out pretty great. And also, we did that with the smallest PV array of any team. Let's see if I can advance one more. When we look at the next team down the list, Team Austria, who won the competition, their PV array is 2.63 kilowatts bigger, but they produced about 3 times the amount of PVs that we did. Still used a little more power than we did, but not considerably much. In terms of affordability, the Delta T90 house came in first. Technically, we tied for first with 2 other teams because if you, per competition regulations, if your house is under 249,000, you take first place. So there were 3 houses that came in for under 249,000. Our house, though, was the least expensive of the top 3 by a factor of $63,000. At the end of the competition, the team and the house received the Byron Stafford Award. So Byron Stafford was one of the original competition organizers and was the site operations manager on the first competition. And I think the competition organizers recognized what the mission of the project was and what the mission of the team was was to show that we can get all this high performance in an affordable, really delightful package. So then after the house was broken down for the competition, we sent it to Springfield, Ohio, and it's sitting next to the Frank Lloyd Wright's Westcott House at the Westcott Center for Architecture and Design. It's sitting on a series of helical piers. The site that we had for the house was on disturbed fill, so we couldn't really get into a lot of expensive excavation and then bringing fill back in. So these helical piers were a relatively quick way to address this site. And since the floor of the house is insulated appropriately, there wasn't really a big reason to put it on a frost-protected wall or a typical concrete foundation. So you can see the insulated chase for the plumbing coming up out of the ground. It's going to be right here. So this is after a year on site. You can see that we're starting to get some staining on the house. This house sits on a really busy intersection in Springfield, actually on the Avenue of the Americas. So there's a lot of vehicles and a lot of heavy trucks stopping at this intersection. So we're thinking that maybe the pollution is landing on the gap in the rain, between the boards and the rain screen, and then washing down the wall. Detail of the window. One thing I learned about working with a group of new carpenters, of learning carpenters, is that especially on our team, they really wanted to make everything the best they could, and their mindset in that was to make everything really tight. So, like for instance, on the sill boards here, everything is super tightly placed. Had we jacked this up probably 3/8 of an inch, because it's all completely water sealed in back of this board, we wouldn't be getting the staining and the eventual rot that we're going to get on a board like that. So this is what the house produced. This is how it performed after the first year in Springfield. So we can see the actual kilowatt hours of consumption was about 3126, and that goes from April 14 to April 15. 2015, and then we can see what the PV array actually produced, and this is also from the middle of April up until the middle of April, from 2014 to 2015. So it produced more than it consumed, but there's little hot water demand in the space. So there isn't actually anyone living there. It's being used as a classroom and a facility for teaching. So it basically sees really high demand over a period and then no demand. However, the space heating was constant throughout the year, and we'll take a look at that data. And then this is what the PV watts calculator estimated it would use. Or I'm sorry, what that PV array would produce in Springfield, and we attribute the difference to snow cover on top of the array. Remember, the array is flat on the roof, and I oftentimes get the question, well, gosh, what about isn't it better to have them pitched at at the optimum angle of 45 degrees in Vermont for let the snow slide? But I have this big, pretty dense archive of images of, snow-covered PV arrays, facing pretty steep with, covered in snow. And if it's true, the snow will eventually slide off of here faster than it will off of this flat roof. But when we look at the actual gain that we can get in the cloudy winter months in New England, it's not really that big of a difference. And so we blower door tested the house after the first year, and this is what we saw. So if you remember, we thought we were going to, because of all the obsessive air sealing that we did, that we would get 0.3 air changes per hour at 50 pascals. We ended up getting 3.82, which means that we actually had a really leaky house. Lesson here was, of course, blower door test early and often. we went around the house and started looking for air leaks, and some were poking up in the window corners, really minor, a couple in the corners of the building, maybe more thermal bridging here too, but nothing serious. And then we took this shot down here in the lower right corner, and that's the access chase, the access panel that connects the east module to the west module. That was sealed up with a brand new floor, so to get at that, to air seal it, means pulling up the new floor. Here's that access chase. We also found some leaks around the skylight. The skylight was not shipped on the house, so it had to get installed after the fact. And after the house made it to Ohio, some additional plumbing lines were run and not sealed up. Some electrical outlets were added and not sealed up. And then also the heat recovery ventilation units, you can see them in service here. So this one is probably pulling in fresh air, cold air, and here it's expelling warm air. We're thinking also that we were getting some breaches from around those. And so after we corrected the house and filled all those gaps, blower door tested it again, got it down to 1 air change per hour. And so if we look at the standard, passive standard, we're at 0.6. But look at the difference in the amount of heat loss that we're getting just by air sealing. And again, this is where we projected we would be. So we still have some more air sealing to do. But the interesting thing is that with the 3.82 air changes per hour at 50 pascals, we were maintaining this average indoor temperature through the heating months of 69 degrees. You can see it's a little below the comfort zone in February. Staying pretty good throughout the rest of it, but the average indoor temperature 69 degrees at 3.82. And so that's how much electricity we consumed maintaining that interior air temperature. And so the percent time the interior temperature was above 72 was only 12.62%. It was below 68 50% of the time, and it was right in the comfort zone about 37% of the time. But if we just move just to show you what the margins are, if we go between 75 and 64, we're in that zone about 99% of the time, 98.6% of the time. The house is staying super dry. What we think is happening is that these the HRVs are basically taking any humid air in the winter and dumping it to the arid cold weather in the winter, and then in the summer, basically the house is open a lot. So this is showing also what the just a spreadsheet for later if you want to look at it, what the interior relative humidity is, and the interior temperature, and then the average exterior temperatures. So the interesting thing here is that if we consumed 3126 kilowatt hours at 3.82 air changes per hour, what would we have done if the house was actually air sealed properly and was at 1 air change per hour? And we think we could bring that down to about 2,000, or in the neighborhood of 2,000 kilowatt hours just for space heating alone, and our production stays the same. So here's a few shots of the house in situ in Springfield. I'd mentioned that if anyone is interested in seeing the house, it's open for tours often. So I would contact the Westcott Center for Architecture and Design in Springfield, Ohio. Not only would you get to see this house, but you would get to tour Frank Lloyd Wright's Westcott House. It's an extraordinary facility. So that's it. Be happy to take some questions if there are any.
Hey, Matt, that was really a terrific presentation. Just amazing. So I've been watching the questions as they've been coming in, and there are dozens of them. So, but some of the questions that were asked early, you answered towards the end. So I'm just going to scroll through the list. So we really have about 5 minutes for questions.
Okay.
And so what we'll ask is, what we'll try to do is send you the whole list of questions, and you can answer as you see fit. And then one of the organizers can then send it to really everyone that was registered for the webinar.
Okay.
So one question was, why was dressed lumber chosen instead of truss joist or similar kind of manufactured framing?
Right. Well, that was, that was really under the direction of the modular manufacturer that we were working with. In their experience, engineered lumber like I-joists and things like that, they haven't found them as how do I say this? They haven't found them as forgiving as the conventional lumber or dimensional lumber. And using this dimensional lumber, it's what they've found is that when it comes in graded and stamped with showing which directions the crowns go, it's just as easy to work with. So everything is straight. Everything there aren't any wanes or cups. It's all really high grade lumber. I think it probably adds a little weight to the house, but it's really what they found works best for their system.
Nice. Here's another question: is the only attachment from the drywall to the studs an adhesive material? And assuming that the answer is yes, don't you have any shear or lateral load requirements that need to be met? And then along that same lines, with stiletto bracing, how do you keep the drywall from cracking during shifting?
Okay, yeah, that's a great question. Thanks for bringing that up because, I didn't mention the drywall after it's, like, for instance, on that roof system that I showed, it when it's lifted into place, it is screwed afterward. They do screw the sheetrock on afterward, so it has both an adhesive and it's screwed. And I think that helps quite a bit with cracking also, because it basically has this big bead of sealant connecting both sides of the rafter to the sheetrock. This house was each module weighed I think the east module with the kitchen in it weighed about 35,000 pounds, and then the west module weighed about 30,000 pounds. They're pretty heavy duty, but there's also a lot of plywood on it too. So the underside of the floor is decked with plywood. The walls and the roof are all decked with plywood. So there just wasn't a lot of racking. And to keep in mind, this house has about 5,500 miles on it, and has been crane lifted 1, 2, 3, 4, 5 times, and there just weren't a lot of cracks in the sheetrock. Very, very, very minor.
Thanks so much. Someone asked if you could provide, if you're willing to provide the name of the factory where the houses were manufactured.
Yeah, I can do that online.
Yeah.
Oh yeah, it's Huntington Homes in East Montpelier, Vermont. Like I said, they've been in business for 35 years, and they really make a great product.
Thank you.
Yeah.
Let's see. Someone asked why you chose the type of siding that you chose rather than a manufactured siding, like a cement board siding.
Oh yeah, we were the project really wasn't didn't only have an eye just on affordability, but it had an eye on making a project or a product like this locally out of local materials as much as we could. and employing local people. So, the big vision for this place was that these houses would start being produced in East Montpelier, and the siding would be milled in East Montpelier, it'd be harvested in Vermont. So yeah, as much as we could, we tried to make use of the great palette of materials that we have in the Northeast and in the trades that are here. The whole wall system is, it's a bio-based wall system. So it's, there isn't any foam, very little plastic in the house. Yeah.
Well, thank you so much. So we actually need to wrap it up, but I have a few parting words here. So one of them is that we will send you these questions, and again, you can answer them as you see fit, and then we'll disseminate them to those that have participated in the webinar. Also, this does conclude this AIA CES course. The webinar survey report from the URL will be sent to you in a follow-up email in the next hour. So you need to complete the webinar survey report by Friday of this week in order to get your continuing education credits. And you can learn about other AIA web offerings at network.aia.org/events/webinars. But I really want to thank Matt Lutz for this terrific presentation. And I also want to thank two people who are behind the scenes, Garrett and Linda, who really make all of these webinars possible. But thank you so much to Matt, and look forward to connecting with everybody next month for our next webinar. Take care, everyone.
Thanks.